All right. So I'm going to first do the problems that people had specific questions about. So I got a few emails yesterday, today, specific problems to do, and then whatever time's left, we'll do whatever questions I haven't covered. So, first question that I got was off the review packet. Alright, so number 7 off of the practice problems, review problems. Alright, the question states, alright, so the question is, I shortened the actual question, the real question is worthy. So the Kc for the following reaction is 1 times 10 to the negative 5th. If the initial concentrations are 0.75 molar of N2 and 0.75 molar of O2, what are the equilibrium concentrations? So what are some key words? There's like 3 key words that tells us what kind of problems we need to do. Initial, equilibrium, and you're given Kc, right? So you're given Kc and it has the words initial and equilibrium in it. So what do we need to do? Ice chart, which has the words initial and equilibrium in it. So those should be dead giveaways as to what we need to do. Alright, so we have an ice chart. Are we in the correct units to do an ice chart? Yes, right? We're in molarity already. Alright, so 0.75 and 0.75. What do I have initially at the NO? 0. Okay. Alright, what happens here in this change column then? Okay, minus x over here. What about this guy? Minus x. What about this guy? Plus 2x, right? Because there's 2. 2x. Alright, so then alright, so now we have this set up. What's the big K called? Like, what's its name? 2 words. Equilibrium constant. Like, we're given the equilibrium constant, and that value is 1.0 times 10 to the negative 5th. So what do I put on the denominator of my fraction? Okay, okay. 0.75 minus x, 0.75 minus x. What do I put on the top? 2x squared. Why is it squared? Because I have 2 products. If you had not squared this, you realize you would be in trouble in about 2 minutes because you would have a quadratic. There are no quadratics on the exam. So if you get to the point that you're like, crap, I have a quadratic, you've screwed up. Somewhere you lost a square. You've definitely made a mistake. Back up. There's nothing on the test that requires that. I see lots of quizzical looks. Let's back up. Hang on to that thought. I see lots of people going, I don't know why it's squared. Let's back up then. Finish the problem if you've got it, but if you're confused, let's look at this. right? That's our equation. Yeah, I see lots of people going, what the? This is from chapter 15, so I realized it was like years ago in your memory. Alright, so if I wanted to write the equilibrium constant for this reaction, it's what over what? Products over reactants, right? And so the reactants are this. And then what do I do about the factor of 2? Right, that's why it's squared. Right? But then when you combine that with an ice chart, you had 2x, and now the 2x is squared. Right? So you should have both types of 2s, big 2 and the coefficient 2. 2s and 2s and 2s. It's 2x because these x's are 1s because their coefficient is 1. But I need to add twice as much because I make twice as much. Yeah? So it would look like this. Right? Now I have the top that's squared and the bottom that's squared. How do I solve this conundrum? Square root it. Alright. What is that? Do you want me to keep solving? Are you guys confident from this point on? Just finish it? Okay, I'm like 3/4 there. What would be my next step then? Because it's not an acid-base reaction. Yeah, there's no acids or bases in this question. Are they? Yes. There should be. Yeah. They should, in theory, always balance. And have I answered the question? The question was, what are the equilibrium concentrations? Does this tell you the equilibrium concentration? No. Really close to being done, but this is not the final answer. How do I find the equilibrium concentration? I had to plug them back up into this, right? So I would do 0.75 minus this, 0.75 minus that, and then double that. So into what is that? I think it's the same value, right? It's right. I mean, it'd be 0.7. You use sig figs, right? It'd be. Yeah. I mean, it's changed nothing. All right. Questions about this one? All right. Let me move on to my next question then. Let's see if I can scoot that all up so you can keep looking at it while I do the next one. Go 7. Alright, we ready for the next one? Can I move my sheets of paper? Alright, so the question is, given that the kW at 30 degrees Celsius is 1.47 times 10 to the negative 14th, what is A, concentration of hydroxides, and B, the pH of the solution? What is kW? Equilibrium of water, right? It has a little w, which specifically tells you it's water, right? And so if it's the equilibrium constant of water, what are the reactants? Water, right? So kW refers to this, right? It seems crazy, but I'm going to write it out and you're going to be like, oh, I can make you can make a lot of shortcuts in this question here in a second. If I was going to write the kW equation for this, what goes on top and what goes on bottom? Product of reactants, right? And so we have this. Yep. Oh, this isn't balanced. What goes on the bottom? Well, it can't be nothing. That'd be 0 in that calculator anger. 1. Why is it 1? Because water is 1. The same reason we always just draw a line through it. Right, the concentration doesn't change. So what is kW actually equal to? Just hydronium times hydroxide, always and forever. Like in Greece, always and forever. And you sing a little song and dance. Sha-na-na-na-na, right? So if you don't know this off the top of your head, circle it, star it, remember it. kW equals hydronium times hydroxide, always. So, if I know kW, how do I find these concentrations? What letter should I put in their place? If I know this, right? Because if I put in the ice chart, it would be this, 0, 0, plus X, plus X. So kW is this value equals, so now how do I find X? Square root, okay, let's see what that is. I could have done an ice chart and gotten to the same point, but if you note this relationship, it's much faster, obviously. Did I drop it? Yes. 14. Sorry. That obviously changes my answer. Yeah, just add 1, right? Oop, nope. Yes. In fact, you can. Yes. Yes. Very, very slightly more acidic. It is. Which is also why, to a total different tangent, really cold water is also a little more basic. So ocean water, is that not right? Hold on. I got on my tangent. Hold on. Here we go. What's that? 2, 4, 6, 7. Okay. That makes more sense. Okay, good. So, ocean water has a pH of 8 because it's so cold. Ocean water has a pH of 8 because it's really, really cold. Yes, so where it's really hot, ocean water is really acidic. Where it's really cold, ocean water is really basic. And it's because the equilibrium constant is based on temperature. And so the temperature of your water will change the pH of the water. Yeah, which is why like the Mediterranean Ocean and other oceans that are really warm are a little more acidic, and different things can live there and grow there than like the Pacific Ocean, where it's freezing, or the Arctic Ocean, freezing. It's more basic. Different things live there. Real fascinating. So, Total tangent, but a fun fact to share on the weekend. Be like, hey, the pH ocean water is 8. Oh. The Dead Sea, that is trickier because it's so salty that we have to take into consideration some other effects. But the Dead Sea should be, let me think. Yeah, 1, it's really warm, and 2, it's really salty, so it's going to be a little on the acidic side. Still, yeah. We could calculate that. Okay, all right. Include some activity coefficients. No, okay. All right, does this answer part A? Yes. How do I find the pH? Yeah. All right, so how do I find, so this is, right, the concentration of OH minuses. Right, so that's part A. But 1.21 times 10 to the negative 7th is also the concentration of hydroniums. All right. So what should that be? Yep, negative log. Ooh. It's like 6.9, but yeah, we usually call it 7. Yeah. Good double checking. Questions on KW? It's the negative log of that value. Yeah. All right. I had several people ask about this one. Yeah. It would be the same value, and that's why it doesn't quite add up to 14. Like 14 is what we use in our head. It's maybe like 6.9 plus 6.9, which is 13.8 or something like that. So it's because there's some other things that are going to happen in there when it gets really warm. That's all right. So I had several people ask about this one, so we'll make sure we do this one. Yeah. Of what? Acetate? Acetone? It wouldn't really have a pH because it doesn't have any hydronium. Right? So acetone is a organic solvent that does react a little bit with water, but it's going to be, yeah, it doesn't really have any free hydronium thing now. Oh, you're totally fine. Yeah. Nail polish remover. You're good. I'd be more concerned if it was like some of the other crazy solvents we use. So just as strong. And then use your process of deductive reasoning that if it's not as strong, it must be weak. Your scientific intuition, if you will. Which we're finally honing to a point, right? All right, so what are some key words in this question that tell us what to do? Buffer and addition, right? So I have a buffer and I have the word addition in there. So what do I need to do? A few different options of what we could do first. It doesn't ask for it, no. What? Yeah, what kind of chart do we need? It has the word addition. An IACE chart, right? So if we need an IACE chart, what do we need to know about it? Moles. We need to know the moles. All right. Alright, so how do I figure out, I tried to make the problem real straightforward. How do I find the moles of HF and the moles of NAF? Divide by 1. So we're done. Good. Okay. Alright, how do I figure out the moles of HCl? Pretty much the same thing, right? It's going to be 1 divided by 0.1, so it's going to be 0.1. Oh, sorry, I said divide. I meant multiply. No, don't freak out. I've been doing advising straight all week, and so I'm all out of good ideas. I've given them all away to all my advisees, so I'm sorry if you have advising today. You're not getting the best version of me. So you should have signed up earlier in the week. Alright, so I now have all the moles. What do I need to set up my chart now? I need an equation. How do I know what two things are the reactant? Right, so definitely the thing that's being added should be a reactant, right? And so I'm adding HCl. What is HCl? Strong acid, weak acid, strong base, weak base. Strong acid. If you don't know that, something to study for the weekend. HCl, strong acid. If it is an acid, what must it be added to? A base. Which one of these remaining items are a base? NAF. Why did I write HCl as hydronium? It's a strong acid. It exists as hydroniums, okay? What happened to my sodium? I took it out because I don't care about it. Sodium. Lame. Boring ion. Until next week, in which point it'll be super important. But for now, it's just a spectator. It's hanging out on the sidelines going, go titration, go titration. Right? So sodium ions are always spectators. Just exit out. Sodiums are spectators, and they're cheering on the reaction. Go titrate. I imagine if they use their little plus sign, it's like their pom-pom. Go team. Okay. So what should I make now? I'm going to make HF. And then what's left? Water. Alright, now we're ready to just plug it in. Alright, so doing all my clever adding and subtracting and whatnot, at the end, what is now hanging out in my solution? I have an acid base. How are they related? They are conjugates. If they are a conjugate acid-base pair, what are they? A buffer. If I have a buffer, I can go straight to the HH equation. What's the one thing that I need to calculate real quick in order to use my HH? Right, I gave you the Ka, but we need to find the pKa. How do I find the pKa from Ka? The negative log. .46. Now we can plug that in. Does this pH make sense with what you have added to the solution? It does, right? It's more acidic. You added strong acid, so now your pH is more acidic. Good. If you answer that question to yourself and you find it's going in the wrong direction, what do you think the most likely thing you did is? Yeah, you put your fraction in upside down. So ask yourself, oh, am I going in the right pH direction? And if the answer is yes, great. If the answer is no, chances are you flipped your fraction. Just go back and double check to make sure you got that right. Let's see here. The last two questions on the practice exam ask about molar solubility. Those are on the next test. So 24 and 25. Skip. Those are on the next test. Jordan. Correct. For the Henderson-Hasselbalch equation, doesn't matter what the reactant is because it's based on that equation. Yep, but that's a good point. If it wasn't a buffer, we'd have to use the KB.
Okay, so it's the HH equation.
Correct. Always. Yep. When it's not an equation. When it's not a buffer.
Okay.
When it's not a buffer, and you start with a base. Yeah, when it's not a buffer. If you see buffer, always this.
Okay.
Yeah. Alright, let me see what else I had. Alright, questions on this one before I move on to another problem? Okay. It was out of the textbook. Someone was doing the practice problems and had a question about a textbook question. This should be, I think it's chapter 16, number maybe 5. We did. The 5% rule is percent ionization. Right, so you're determining percent ionization. So we always assume, but we can calculate it. Let's see. Alright, so out of the textbook, you were doing some of the practice problems. This is number 5. So percent ionization, we've been calling it the 5% rule. Mastering goes back and forth between the 5% rule and percent ionization. That's all I'm calculating. How much of my reactant became ionized, became product. So what is percent ionization of benzoic acid? We'll just do it in water. Then we'll do benzoic acid when it has its conjugate base in solution also. And when we set these problems up, it looks complicated. You were like, oh, I totally know how to do those problems. Alright, so I'm just going to call benzoic acid HA, right? Does it matter what the structure is or how many letters it has? Why would I make sure that it has an H? What does an acid have to do? Give away an H. So make sure when you write it down, there's an H for it to give away. If it's in water, what's the other reactant? Water. Okay. If it's in water, it means it's reacting with water, which is, I know it's not a reaction, but it's the other reactant. Then what do I make as my two products? This guy and that guy. Am I adding anything to the solution? Oh. There we go. Am I adding anything to the solution? So what kind of chart should it be? Plain old ice chart. I forgot to write up here, but the Ka for benzoic acid. 10 to the negative fifth. Alright, so what goes on the top of my fraction? X squared. What goes on the bottom? Yep. Can I make an assumption that X is small in this case? Can I make this assumption X is small? Why? It's an acid-base reaction. So I can make the assumption that X is small. Which means I will rewrite this as that. Alright, so then 6.5, negative 5, 1.5. Alright, I want to find that percent ionization, which is the same thing as the 5% rule. So how do I figure out the 5% rule? What do I do now? Yep. Percent ionization, 5% rule, same thing. Yep. Alright, so if this was a different kind of question and I said, does the 5% rule hold? Is X small a good assumption? What would you say? Yes, it's a good assumption, right? 2 is less than 5, so good. In this case, it's asking, this was actually what it was asking for. It's asking for that value. It was asking for the percent ionization, just 1, 2%. Chris? It's going to depend on how the question's written. I could ask for either one. I could say, what's the percent ionization, in which case you do it here. Or I may ask, as soon as I write the exam, does the 5% rule hold? In which case you would calculate and say, yes, X being small was a good assumption. So, yeah. If we kept the X, it would change a little bit. Yes. Yep. That's what it's saying. It's like, as long as the change is less than 5%, it's considered insignificant statistically. So. Alright, so then, part B is, what if there's now if it has conjugate acid and base, it has now it's a buffer. Alright. So we'll change things up a little bit. Look how clever I am. I can use my same chart. Alright, so the reactants and products haven't changed, but now I have two things in there initially. Right? Now I'm saying I have sorry. Alright, so, right, I would still do minus x and plus x plus x. Alright, so now we have this kind of problem. How do I go about solving when it's set up like this? All of the x's or just some of the x's? Just the plus and minus x's. Otherwise, there's nothing left to solve. Right? If I get rid of all the x's, catastrophe. You're x-free. There's nothing to solve for. Alright, so we're going to say 6.5 times 10 to the negative fifth is 0.1 times x over 0.15. Because we assume this x and that x are small. Alright, I haven't done this problem yet, so someone double check me, but I think I'm good. Let's see, what was that? 2, 4, 5. Alright, so the same question. Now, how do I figure out the percent ionization? Which one do I compare it to? So the Ka is calculated from the HA, so we need to compare it to the A losing stuff rather than the A minus gaining stuff. Right, so I'm trying to figure out, the assumption is that the reactants don't lose very much, and so I want to compare it to how much it could have lost, if that makes sense. Compare it to the reactant. Let's see what it's down. Alright, so in this case, the percent ionization is 0.065. In my original case, it was 2. Why? It's a buffer. What does Le Chatelier's tell us in this case versus this case? So in this case, I have no product. So what has to happen to my reactant? It has to shift which direction? To product. So I need to have a lot of it ionized to make product. What happened in this case? I have some products. They're not equal, so it's still going to shift, but doesn't need to shift as much. No, right? Because I have products. I don't have a lot of products. So it's still going to shift the products, but it doesn't have to shift as much. It only has to shift 0.065%. That would be a great test question. Just saying it combines a lot of things. Acids, bases, buffers, Le Chatelier's, K. Good stuff in there. If I can remember that long enough to go upstairs and write that down, that'd be a great test question. Chances are I won't. I'm now the absent-minded professor who doesn't remember anything. Alright, those are all the ones that people emailed me about. Are there other questions or question types I haven't touched on that you would like to look at? Oh, yeah, sorry. Number 5. The answer key is wrong. It should be, I think it's D. D. I believe that's true. Sure, yep. Let me get out my example. told you the wrong answer. It's C. Yep. Sorry, I tried to read it real fast. Yeah, now I've read all the options, it's C. Alright, so again, what's K represent? Equilibrium constant, what's Q? Yeah, anything but the equilibrium constant, right? You're anywhere except at equilibrium. But they're defined the same way, right? So if I have right, they're defined the same way, but we have to figure out where we are in relationship to each other. Alright, so how do we know that C is a true statement? I'm working backwards. Right, when they're equal to at equilibrium, by definition, C is true. Okay, that's definitely true. Alright, so let's look at A and B and figure out if those are true or not true statements, because as soon as one of them is false, then we know it can't be D or E. Right, by process of elimination. Alright, so let's look at, I guess we'll look at A. If Q is less than K, ignoring the second half of the statement, if Q is less than K, then do I have too many products or too many reactants? If this value is smaller compared to this value, do I have too much numerator or too much denominator? Too much denominator, right? For this value to get smaller, you have to make the denominator bigger. So if the denominator is bigger, what do I have too much of, reactants or products? I have too many reactants. So do I want to form more reactants? No. We'll do the opposite case, just in case you chose B first. Alright, if Q is greater than K, does Q have a bigger numerator or denominator? It has a bigger numerator, right? Bigger numerator, which means it has more reactants or products. It has too many products, so what does it need to do? Well, yeah, more reactants or less products. Both of which are not what this says. Okay. Alright. Other kinds of questions I haven't done? Yeah. Yeah, let me find it. Oh, that's an excellent one too. I had done that one, I just forgot to put it down. Alright, so chapter 15, number 53, right? I think you had one of these on your homework. Something like this. Alright, so let's think through what the question's asking us. First of all, what is KOH? Strong base, right? So, do I need to write out an ice chart? No. No ice chart. It's a strong base. It only does one thing. Right? It's already kind of at equilibrium. You can think about it that way. What units do I need to be in to solve for pH? Molarity, right? I need to be in molarity to find pH. And I was given that it was 3.85% by mass. Oh, I forgot the other thing. Is that. Alright, if I want to use a percent sign in math, what do I need to do first? How do I get rid of the percent sign? Divide by 100. Okay. if I want to end up in units of molarity, what does molarity mean? What over what? Moles over liters, right? And we have right now grams over milliliters. So that's a good starting point, right? If I want to end up in moles, what do I have to figure out about KOH? It's molecular weight, right? Because if I'm in grams and I want to figure out moles, 1 mole how close are we to molarity? Pretty darn close. What do I need to do to get into a molarity unit? Convert milliliters. So how many milliliters in a liter? 1,000. Alright, so now we have molarity KOH. What next? If I want to find pH, what can I do right this second to get me on the way? POH, right? Write it down. So then how do I find the pH? It is very basic. How do you know this is a good basic pH? You're using KOH, so this should make sense in terms of a basic pH. So. Alright. If you email me over the weekend, I'm just slow at getting back to you. I will eventually get back to you. That's just a slower process. If not, go Team Chemistry. Yay! Pep talk, pep talk. Alright, see you Monday.